this video, we will cover the topic of PID controller. To understand the content of this video, it is recommended to go through the previous videos to understand the definition of PV, SP and OP. We will be covering three topics which are proportional term, integral term and derivative term of the PID controller. We will use the tank level controller to demonstrate the basic principle of proportional action. In steady-state process, the level of the tank PV matches the set point, which is 30%. In this stage, there is no error. Thus, the control valve opening percentage do not need to be adjusted. Let us evaluate the controller's action when there is a disturbance. For example, the inlet flow increases and cause the tank level to increase to 60%. At this point of time, PV is no longer matches the set point SP. The difference between PV and set point is the error. Thus the error now is 30%. When there is an error, the controller will increase the valve opening OP in proportion to the amplitude of the error. When the valve opens more, the tank level PV will reduce back to the set point SP. The equation of proportional action is basically Kc times the error. Kc is the proportional gain. This is also known as controller gain. In other words, proportional action generates an output correction that is directly proportional to the error. Some controllers use the term proportional band or PB. Proportional band is calculated by dividing 100% with the proportional gain. In this diagram, we will evaluate the effect of increasing the controller gain when the error is 10%. If the controller gain is 1, the controller will generate an output change which is same percentage of the error. In this example, since the error is 10%, the output change is also 10%. When we increase the controller gain to 2, the output change will be 2 times the error. Thus, the output change now is 20%. When we increase the controller gain further to 3, the output change will be 3 times the error. Thus, the output change now is 30%. Let us observe the process behavior in an actual process controller when we vary the controller gain. In this example, when the controller gain is 1, the process variable PV take a long time to achieve the set point. When we increase the controller gain to 1.5, the process variable PV react faster and achieve the set point faster. Increasing the controller gain too much will cause unnecessary process instability. In this case, when we increase the controller gain to 2, oscillation starts to occur. This is an undesired condition. Proportional-only controller has a shortcoming as it has tendency not to settle at its set point. Even after long duration, offset to the controller set point will still occur. In this video, we have learned that proportional action of a controller will compensate for error due to process disturbances. However, proportional-only controller has a tendency not to settle at its set point, thus creating offset. What will be the solution for offset? The answer is in the next topic, which is introducing integral action to the controller. In the earlier example, we have learned that proportional-only controller can generate offset. When offset happens, what can we do to eliminate the offset? This is where the integral action of the controller comes in. By introducing integral action, the offset is eliminated. Integral action of the controller generates an output correction that is directly proportional to the accumulated error over time. Mathematically, this is defined as the integration of error. A constant Ti or integral time is applied to scale the output calculated. Unlike controller gain, integral action is defined by a certain repeat over time or in the unit of either seconds or minutes. When we want more integral action, we will increase the repeat over time. Repeat over time is also known as reset gain or reset rate. If we want to reduce the integral action, we will reduce the reset gain or reset rate. In a lot of controller, the terms integral time is used instead. The integral time is in the unit of minutes or seconds. It is basically means minutes or seconds per repetition. When integral time is used, increasing the integral action will means reducing the integral time. When we want to reduce integral action, we need to increase the integral time. Thus, the relationship is reversed. In this example, let us evaluate the effect of changing integral time. When the integral time is only 1, we can observe a huge offset. By reducing the integral time to 0.7, the offset reduces. When we reduce further the integral time to 0.1, the offset is eliminated. We need to be cautious not to use too much integral action, as this might cause unnecessary instability to the process control. We have completed the topic on integral term of a PID controller. Now, we will cover the topic of derivative term of a PID controller. In slow process like temperature control, the process variable PV might take a very long time to achieve the set point. By introducing the derivative action, the process will react faster to reach the desired set point. However, we need to be aware that introducing excessive derivative action can potentially cause unnecessary process instability, which we do not want. Derivative action can cause instability for fast and noisy process. Thus, derivative action is applied only for slow process like temperature controller. For noisy process variable PV filtering can be applied to reduce the amplification of noise by derivative action. We have completed the topic on the PID controller. In next video, we will learn how to tune a controller.